This talk is kind of a confluence between an academic talk and an industrial talk. There's unfortunately a big difference between academically useful algorithms and industrial useful algorithms. And so this one is going to focus a bit more heavily on the industrial side of things. And just as a preview for the last slide will have a link where you can get all of these slides and other resources as well. Some of the resources you can't get via the link are hats. I'll be giving these out to the first two good questions that we get at the end. And most questions are good if they're bold. And then we have a number of other books which talk about some of the issues here, one on anomaly detection, one also on an interesting form of data security. Those are back there, and those are part of a series that I've been working on with my co-author, Ellen Friedman. So as mentioned, I'm Chief Application Architect for MapR. As not mentioned, I'm also a committer and project management committee member on a whole bunch of Apache projects. And a whole bunch means I can't remember which ones. I have to look it up when I need to know. And I'm also currently serving, this is a rotating post, as the VP of Incubator for Apache. This is how projects come into the Apache Software Foundation. This is how new things like Flink and Spark and others come in and become real Apache projects. So it's an interesting position to be in because there's so much happening in this community right now. There's a couple of hashtags. There's probably a hashtag for this meetup, but I didn't know it, so I didn't put it on there. My apologies. So today what I want to talk about is the meaning of what is important. It's really important to think about what you value in terms of algorithms. What different algorithms will have different kind of value to you. There, that's the one I meant. And I want to talk a little bit about why that is. What it is that makes something important to each of us. And I want to talk about the differences, and then I want to give some examples of what I think are industrially important algorithms that fit the criterion that I talked about. So to me, having some experience in these things, I think being deployable, robust, transparent, skill set and mindset matched, and proportionate are the important characteristics that I was able to come up with. By deployable, I mean that if I were to do something extraordinarily clever, I try never to do that anymore. I did that early in my career and quickly became indispensable, which was a disaster because I was indispensable in the middle of the night. I was indispensable on weekends. I was indispensable when everybody else got to go on vacation. That was one of the worst, stupidest things I've ever done, is to be clever. And so I never try to do that anymore. What I try to do is be clever enough to build something that's simple, that can be deployed, that can be standardized, and can have repeatable processes. I think something has to be robust and transparent. Robust means somebody else is going to screw it up. They're going to misconfigure it. They're going to turn the knobs to the right when I say turn them to the left. The system still has to work. And when it's misconfigured like that, or when it is correctly configured, you have to be able to tell what it's doing. So that when they turn the knob to the right, they can see it start turning red. They go, oh, I'll turn the knob the other way. He said turn it left, but I'll turn it left. That sort of thing. And so the robustness and transparency go hand in hand because the ops team will be able to tell what's going right or wrong with the system. I also think that it's very, very important for a system to match who's going to be running it. I learned the hard way in me trying to do operations that I don't have the right mindset for it. It's fun, it's exciting for about 4 weeks. And then it's boring and hard and not what I want to be doing. So I found that I'm the kind of person who makes a list of things to do so that I can find the ones that I want to do. I do 20% of the list I make because I'm a cherry picker. I find cool stuff to do. I invent things. I look for novelty. Novelty seeker is the word for that. That makes a bad operations team. That's not what I'm good at. On the other hand, an ops type personality is a person who makes a list and they get excited about ticking off every item on the list. It's a very different mindset. They get excited or happy, not really excited, they don't like to be excited, they get happy when things work the same way, when they know what's going to happen. That's the operations mindset. I get unhappy when I know what's going to happen because that means there's nothing being discovered. So we have these two different mindsets. I'm going to build something, but they have to run it. And so I have to match whatever I build to whatever they'll run, reliably, boringly as possible. We do not want excitement in that phase. We want it to be reliable. And we also have to figure out how we can have the biggest bang per minute of effort. Not hours or months or days, but literally, what am I going to be doing today that's going to be making a difference? Not what's interesting necessarily, not what's most geekily, cred trading sort of fun, but what really is going to drive the needle to a better place. So that's what's important to me, but that is in contrast, very strong contrast. Just like the ops goals are different from the inventor's goals, the academic goals are also very different. So in academia, the problem has to be reproducible, and so do suggested solutions. In industry, we have things called trade secrets, and we also have unique businesses. And so what works in my business very well might not work very well in your business. If we could find some reproducible aspect of that, then we'd have to do something different in our businesses to be competitive with each other. That is exactly the opposite of what academia is about. We, in academic sort of research, want to isolate just this important aspects of it. In real life, what we want to do is have as much interaction as possible. Business people call that synergy. In marketing terms, that means that when we do two things together, the result is much larger than the sum. They interact heavily. So it's just the opposite of the academic sort of thing. And the other thing is that in academia, you want to work on novel and pretty hard problems. Easy problems are not interesting academically, and old problems are not usually, old solved problems are not very interesting. And so there's a big stress between the pragmatic point of view and the academic point of view. And unfortunately, of course, most research, most of what you read in papers is the academic point of view, not the pragmatic side. So I'm going to talk here a little bit about building a recommendation engine, but with this very, very pragmatic point of view. How to make it work very quickly, very simply, very robustly, and very easily. So let's think about it. What are the most important algorithmic advances in recommendations? Somebody who's doing research in that might tell you that it's matrix decomposition or co-occurrence analysis. They have all these algorithms that just look at how we look at what people have done and we try to predict what other people have done. Latent factor log linear models, hoo-ha, wonderful temporal dynamics. And I contend that it's none of the above. The most important development in recommendations has been adding random numbers to the results and not doing something stupid like showing all 15 versions of the same video or not showing more than 3 from the same publisher. These have had bigger impact in the dozens of recommenders that I've been involved with than any other advance. Let's talk about them a little bit. See, the real issue in recommender systems isn't actually whether you can learn to do the best recommendation. That sounds counterintuitive. It sounds like, I mean, you're building a recommendation engine. That should be the core part of it. How do you make an algorithm that's as good as it can be? The core problem is that the output of the recommender engine today is the input for tomorrow. The recommendation engine selects its own training data. What you show the person is what you find out about. You don't learn about everything. You only learn about what the recommendation engine has previously shown somebody. And so the recommendation engine actually has two missions, not just to recommend the best thing, but also to show things that might be the best thing, that are near the best thing, that could be something that it's currently overlooking. And that's a mission which is not normally mentioned with a recommendation engine. Another key aspect is it has to be fast. It has to be fast in two ways. It has to be fast operationally, but fast to development as well. The last fraction of a percent is not the important problem. And if you look at how hard people have worked on the last fraction of a percent versus how hard they've worked on these other things, you see a huge dichotomy. The Netflix challenge was Netflix releasing a bunch of data to try to make recommendation engines better. 400 million observations. People from all over the world competed. There were 40,000 entries in this early data mining contest. The goal was to improve the operational systems by 10%. 10%. That's all the improvement. Within the first month or two, they'd already made a 7 or 8% improvement. And then the next 2 years, by 300 different teams, 40,000 entries, they made another 2% improvement. And they beat the 10% criterion by like 1/100 of a percent. Okay, 300 teams of the best machine learning people in the world can make 10% improvement. Dithering, just exploring better, can make 100 or 200% improvement. Just getting better data. Selecting different behaviors can make more than 100% difference. Just avoiding redundant things in the display can make more than 100% improvement. And each of these takes about a week for one person to implement. Which should you do? 300 teams, 2 years, one person, 1 week. You pick. 10 times higher return on the easy thing. This is not good academic research. This is very pragmatic, just do it sort of things. It's not what you normally hear from a reformed academic. So anyway, let's talk about what dithering is. Dithering is randomly reordering the results. Now this is counterintuitive. We just built a recommendation engine that's doing as well as it can to put things in the right order. And now we say that the best thing we can do is to change that order randomly, just kind of stir shit up. Well, in fact, that's guaranteed to make an offline evaluation of the recommendation engine give worse results. But it's almost guaranteed, I mean, it's only empirically, in my experience, guaranteed to give you a very large improvement in actual performance. And it's this today versus tomorrow sort of issue. What we do today is what teaches us what to do tomorrow. So the quote that I hear from all of the people that I've said, try dithering, is they come back to me and say, that made more difference than everything else we've tried. We tried this algorithm, we tried that algorithm, tried different ways of stating things, we changed the UI, and we put random numbers on there, and bam, that made a bigger difference. I'll show you why, but let me first show you how. The way that I do it is a very simple thing. I take the rank, that's R. This looks like math. Really, it's just shorthand. It's not scary, it's simple stuff. So I take the rank, take the log, and add random numbers that are about constant in size. And what that's going to do is when the rank is very small, then incrementing the rank just a little bit, going a little bit deeper in the list, is going to make a big difference in the log. when the rank is really big, making a difference of 1 in the rank is going to make almost no difference to the log. And so when we have a constant sized noise on there, it's going to stir the very deep stuff up a lot, and it's not going to stir the top results up very much. And we can adjust the size of the noise to decide how much we're going to stir things up. And in fact, because it's a log, it's going to stir up result 1 and 3 about as much as it's going to stir up result 10 and 30, or 100 and 300. It has that scaling property, multiplicative scaling there. So it's not that hard to do. And so as I say, the amount that it stirs it up is roughly proportional to the exponential of epsilon. Usually we pick 0.4 to 0.8. Pick a number, look at it, try it. If you don't like it, try a different number. Turn the knob while you're running the system. See if it gets better or worse. Oh, here's a trick. Use like the current time in hours as the seed for the random number generator. What that does is it gets people the comfort of the results sitting still for a little while, and then the promise that they'll change in a little bit. Here's some examples. With epsilon of 0.5, I took 300 numbers and I dithered them. They were originally in order, and here's what the results are after dithering. 1 is the first, 2 is the second. That's the same original ordering. Then I get 6 and 5, and then here comes 3 and 4. So I've stirred up the results, but notice the top result is almost always 1, about 2/3 of the time. And then it's always 1, 2, 3, or 4. But this result is from the first, second, or third decade quite often. And so we've got a lot of stirring going on here. Here's the same thing, but with more stirring. Now you can see the numbers being pulled in are from much deeper in the list. But the first element is still usually 1 or 2 or 3 or 11. So we've got more stirring going on, or less, just by turning that knob. And so you can see what's happening here is things from the second page of results are occasionally being brought up to the first page of results. And if you were to look at click-through rate versus the rank, you'll typically see something like this. Top hits get a lot of clicks, partly because they're at the top and nothing has been seen before people look at them, and partly because you've probably put the best things at the top. But then, at the end of the first page, there's always a precipitous drop because nobody will click to the second page. And so you don't learn anything about stuff on the second page. But if we were to dither things, some of these second page things are going to be on the first page. And we will learn about them. So if there's this fabulous result right here, if we didn't dither, we would never learn that we're almost right. If we do dither, we will. And there's another perverse thing. People will not click to the second page, but they will come back to the first page. What is this we're dealing with? These are humans or something. And because they will come back to the first page, if we seed the random number generator with the time, if they come back, they'll see it's the same if they come back right away. If they come back half an hour from now, they'll see it's different. And they'll think that we've been thinking in the meantime and learning stuff, and we're giving them new things. And in fact, of course, what we are doing is giving them new things, but it's stuff that they would have seen on the second and third page anyway. But they give us too much credit. But the next day, we will have learned from what they saw on that first page, and we will give them better results. So it's an interesting bit of psychology that we interact with the people in an odd way. We kind of tell them one thing and slightly do another, but the result is much better. And give me a show of hands. Who here thinks that this is easy? Who here thinks you deserve a PhD for coming up with an algorithm like that. No, you don't. Because this doesn't advance science. This merely makes one website at a time work better. The lesson here is that exploration is good. Giving good results is good too, but we shouldn't forget that exploration is good. We have to trade off between exploitation, dealing and using what we know, and exploration, learning about what we don't know. There's a trade there, and we really have to do that. This is an important algorithm, even though it is so stupidly simple. Now, here's another example of another way to do dithering. This time, there's real mathematics behind it, and it is done optimally. But it's almost as simple. It's like 5 lines of code, sort of complicated. And you'll see just how easily it is done. So let me show you a video before we go to this. This video shows an example of this trading off exploration with exploitation. Now, what we've got here is a simulation. Because it's a simulation, we know what's really happening. What's really happening is we have 5 coins. Purple here to red there. This horizontal axis is the probability of winning. Winning means comes up heads. This one almost never comes up heads. This one comes up heads just above half the time. If we try this one, we almost always lose. This one, we win pretty often. This one is almost as bad as the worst. This one is almost as good as the best. So now how do we find the best one? We have no way of knowing before we start which it is. We might try it. Suppose we try this one and it comes up heads. Do we just do that because we don't know the others are better? We know this one at least could be heads. Should we try it again, or should we try something else? This is the exploit, explore trade-off that we're trying to make there. So the algorithm we're going to show here trades this off optimally. The curves above this are our current estimates of what the probability is. We've tried blue once. We've already done one thing at the beginning of this video, and it failed. So we think it's kind of on the poopy end of the scale. We don't really know where. We do know that its probability of winning is not 100%. That's about all we know. This is the bandwidth, the fraction of the time we're going to try the different colored coins. And this bottom one, which is a little bit hard to see here, fit to screen, there, a little bit easier to see now, is what's called regret. Now, remember, we don't really know what these numbers are. If we knew, we would just flip red always. We don't really know what they are. But if I were to try green, I have what's called regret. The average value is about 0.25. If I try yellow, the regret is like 0.1. If I try red, the regret is 0. What's the average regret? The average regret starts pretty large here because we know nothing, but we want that to go down as quickly as possible. We want to, on average, be trying the best thing that we can. So if we walk along here, you can see we've gotten some results. At this point, yellow has succeeded several times out of a few trials, and red has succeeded about half the time. Purple and blue and green have failed almost uniformly. So purple and blue and green are all being highly suppressed already, just a few trials in, and regret has been dropped in half because of that. If we go further, you can see that red and yellow are trading places in the leadership, and the probability that red or yellow are showed the most flip-flops. But the lousy ones have been suppressed dramatically. We're getting rid of losers quickly, fail fast, and the regret has dropped even further. Over time, you'll see yellow and red trade See there was a moment there when yellow was ahead of red. Those are just statistical variations to be expected. The system can tell us the probability that it's correct, and more importantly, the system can now tell us the economic value of continuing this experiment. So it's getting better and better estimates here. It hasn't decided conclusively that red is better than yellow, but it has decided pretty conclusively the others are garbage. Now, the difference between red and yellow is not very big, and so it isn't hurt to keep experimenting with yellow. And so that's what the system's doing. And eventually, it does drive the percentage of yellow quite low. So this is the system that I'm going to talk about. This is called a Bayesian bandit or Thompson sampling. So let's continue here. You see how it's trading off exploration? As it begins to know things, it quits exploring on the loser options and continues to exploit the possible winners. This is based on a general algorithm called Thompson sampling. You can look it up. It's actually really simple. It's very near the optimal regret. It trades things off, and it's the currently best known algorithm for this problem. It's incredibly simple. See, it's so simple I could write an integral there. You can skip that. What I do actually is, do you remember we had an estimate of probability on the top panel? It started out very uncertain and over time became much more certain. We could do two things with that probability distribution. We could estimate our best estimate of what the probability is, or we could just sample from that distribution. The estimate would be some central value. The sample could be all over the place. It seems like we ought to be estimating. That just seems like so much more obvious a thing to do. So here we go back to the beginning roughly, nearly. So here I would have estimated red to be right about there. I would have estimated yellow to be just less than that. If I estimated the value, I would never pick yellow again. Happens to be right there, but earlier, right just a few samples before, it would have been wrong, and it would have been wrong forever. And so sampling, where I pick any value in the possible uncertain range of the parameters, is ironically better than estimating. That's the crux of this. I sample the parameters based on the data that I've seen so far, and then I pick the best one, the one that gives me the highest return. It's that simple. Sample instead of estimate, and then just pick the best. Damn. Normally people would say estimate and then pick the best. All we did is change the word to sample, and we get a near optimum result. Here's what it looks like. This is the regret on a simple problem. This is epsilon greedy. This was one of the systems that was recommended very highly just not long ago. And here's Bayesian bandit with a very wrong prior conception of what the value is. And you can see it's about 4 or 5 times better late in the process. Here are competitive, nearly best algorithms. This is epsilon greedy. It's not the best. This is an exploit algorithm where it does just random sampling for a little bit, and then it commits to an answer. It's also considerably worse. This is upper confidence bound, UCB. And you can see that it tracks with the Thompson sampling, the Bayesian bandit, for quite a while, but then it diverges. Then it starts losing out against this. Also, UCB will lose it in very complex situations with lots of alternatives, and UCB also cannot be applied where we have a complicated model of turnout payoff. And so Thompson sampling down here, the Bayesian bandit, wins against all of these options, and it has been shown since this, to be as good as the optimal strategy possible. So this is a form of dithering. When it says sample instead of estimate, it's using random numbers to pick an ordering. It is doing dithering, but it's doing dithering at exactly the optimum knob turning, how much dithering it should be done in order to maximize exploration. And so that's very, very exciting that way. You could use this in almost all these situations. You can't always use it, partly because you don't have time necessarily to understand your system. But if you can, I highly recommend it. So 2 algorithms that have very high practical application. Exploration is really pretty easy to do, and it pays big benefits. Cool? You guys are being very quiet. I presume that it's because you're being very attentive and not that you're asleep. But you, I see, are either on your phone or asleep. So, third example here of a pragmatic and useful algorithm is something called online clustering. K-means clustering is a form of clustering data points into similar groups. But typically, I mean, it's useful for compression, it's useful for feature extraction. It's not usually useful by itself. But it has a problem in that the more data you get, the cost of the algorithm goes up faster than the amount of data you get. This means it's not a big data solution because we're going to get a lot of data. Sampling down the data is not a solution because you lose the resolution that you want. But here's an alternative. This is a so-called sketch-based algorithm where we go through the data very fast to produce what's called a sketch of the data. A sketch which is guaranteed to have the property that if we cluster the sketch instead of the original data, we will get a clustering of the original data. And because we can compute the sketch very quickly, and because the sketch is very small, we can cluster it very fast. The overall cost is the cost of producing the sketch. That's almost all the time. And then we go bing, and we cluster in memory the little tiny sketch. It is as small as the log of the number of data points that we have, which is much, much smaller than the actual data. It's based on a paper by Schindler, Wang, and Meyerson. Meyerson, at least, is now at Google. I think Schindler is as well. But here's a picture of it. Take some fancy data set. If we were to cluster it with a lot of centroids, we can see that this is capturing the essence of this thing. What I created there was a spiral with noise on it. And if we just had picked one of these and then added noise on it, the distribution would be about the same. These 20 clusters have captured the shape of the data. And so I can store the data. I could quantize every data point just back to this nearby cluster, and I would have compressed the data dramatically, 4.3 bits or so per data point instead of 2 dimensions. We could compress it quite a lot, and compression is, in fact, the same as truth. If we have a very good compressor, it is a very good model of what's happening. Or we can use 2 of them or something like that. But it's a good representation. It diagonalizes the data very well. Here's the 2,000 samples I have. And you can see that these data points from along the spiral fit very much into a single nearest cluster. We can do it to other data sets like this. You can see 4 nominal different colored clusters. And you can see these sketch cluster centroids inside there. So this is represented by 5 of the sketch centroids. So what we've done here is we've clustered this data with lots and lots of cluster centroids. That leaves us with a representation of the data, these diagonal or the triangular data points, that give us a good idea about the original data. And the reason that this is good is because the most common way that clustering fails is like this. What happens is we start with some initial conditions where the clusters are going to be. And if I put 2 initial conditions in this actual cluster, and 1 down here, and 1 here, and 1 here, what will happen is these 2 clusters will fight it out over this batch of data. This cluster will move to between these 2 points. And then we wind up with a stable clustering, which is a very bad clustering of the data. A good clustering would have 1 color in each of these groups. This is a very common way to fail. But if I were to try to put 5 times as many clusters in there, I would be almost certain to get one cluster in each one of these groupings. And so I would have a decent sketch, if not a good clustering. And then I could cluster those sketch centroids very quickly and easily. And so that's the idea here, is that we can pass through the data very quickly, making a very slimy clustering with lots and lots of centroids. And we get a good sketch, not a good clustering, but we can convert the sketch into a good clustering. We can also convert the sketch into a lot of other things. There's lots of other algorithms that allow us, that it can be done using this sketch as a surrogate for this very large data set. And so sketching is a general technique which has huge pragmatic implications, but very limited academic input. Sketches make big data small and let us to do very interesting things. Is this interesting yet? Good, good. Yeah?
So in other words, instead of overwhelming your modeling with data, you're using something that can be made comprehensible.
Yes, but you have to reduce it in a way that preserves the delicacy. In big data, we begin to see some very rare phenomena, the edges, the corners of the data. And if we just say, take every 1,000th data point, that will make our data sample 1,000 times smaller, but we lose the nuance. And these nuances can be very, very important. They can be important if our competitors are almost at our own level, so that if we don't get those nuances, they will get them first. That's one reason. Or in some cases, like security, finding all those little corners, if we don't find them all, we will have a catastrophic loss.
So you may have to play with that size.
Well, a sketch is a good simplification of the data that preserves those corners and little dusty crevices. If we don't preserve that, then we can't decrease the size of the data. So I'm going to show another example, 2 more examples coming. This one is what I call search abuse. And it's kind of one of the simplest ways to build a search engine. It will probably not perform as well as the best known algorithms. But if you remember, the things that make a recommendation algorithm very, very good tends to be dithering, anti-flood, finding the best behaviors, not the algorithm. This algorithm, I have evidence, can be deployed in days. Other algorithms are difficult to deploy because you have to deploy special purpose recommender type engines out into production and can take weeks to months. I contend that those weeks to months are better spent implementing dithering and finding better data. And you'll see why I say that this can be deployed so quickly. But I've actually had a bank. Banks are not the paragon of fast development. A bank, after I explained this approach to them, they had a prototype up in 4 days. From Friday, they flew home to New York. One of the guys worked on the weekend. On Monday, I appeared in New York, and they showed me the demo. That's how fast they could implement it. And from zero, no data, nothing, to recommendations in customers' hands on a mobile platform, they were able to do in 4 months. That was with people who are not experienced with big data. So that's fast. That's really fast. So with recommendations, we want to take a crowd and we want to understand what this person in red does and wants and how they think. Now, that does not mean we're going to find some person like this person who behaves just like the person in red. There isn't going to be somebody like that. I like American folk music, some jazz, and Bollywood. You're probably not going to find a person who has that combination. That's not so. And then you add classical music too. That's not right. But we probably do have somebody in the room who likes jazz, somebody in the room who likes classical, somebody who likes American folk, and probably even somebody in the room who likes Bollywood music. And so what we can do is match up pieces of me against pieces of them. We're going to decompose everybody and find things like that. Now, the way we're going to do that is a very simple technique. We can do it in cartoons. Alice has an apple and a puppy. Okay, data point 1. Data point 2, Charles has a bicycle. This will be big data soon, I promise. It's not big data yet. Bob walks in and he's got an apple. Okay, what do we think he ought to have beyond the apple? Of course, a puppy, right? Because Alice got an apple and then a puppy. Therefore, we're going to work from this huge data set that we have and give Bob a puppy too. That's the basic idea, co-occurrence. But who here, when they were little, wanted a pony? You can do it. It's brave. Yeah, see, she's brave. Everybody wanted a pony. I know you did. Everybody wants a pony. Now, if everybody wants a pony and Amelia walks in and says she likes a pony, what else should we recommend to her? We just learned nothing except that she's just like us. She's one of our users. Everybody wants a pony. She wants a pony. Yawn. Give her whatever's popular, an apple or a puppy or something. It's not really a recommendation. It's just a greatest hits type thing. Greatest hits is a good recommender, but it's not really what we're trying to build here. So that's the other problem in recommendation, is there are very, very popular things, ponies, that make it hard to recommend because they co-occur with everything. So we want to find things that co-occur more than we'd expect, co-occur anomalously often. That's what we want to find. And the way we do that is a multi-step process. We start by building a little matrix of all of the historical things that people have done. I should point at that thing sometime, shouldn't I? I'll make the man work here with the camera. And so we build a history matrix, rows, which are people, and columns, which are items. Then we turn that in by adding up overall users into co-occurrence. How often did puppy and apple co-occur? Once. That was Alice. How about pony and apple? Well, that was Bob and Alice. And only Charles had a bicycle, so it only co-occurred with pony once. That's a co-occurrence matrix. It has lots of co-occurrence, which is not interesting because of the silly pony stuff. Only the puppy and the apple, we're pretending, because this is not big data yet, were interesting. So we reduce that to an indicator matrix by deleting all of the uninteresting co-occurrence and leaving just binary indicators on the interesting co-occurrences. Okay? Then we take a search engine. We of course already have, if we're selling products or something like that, we've already got a search engine. It's already got an entry for puppy in this case. It's got a title, a code, a description, keywords, all of that sort of thing. We already have that. So we're going to add one more field. We're going to take that indicator matrix, one row of that, and we're going to put it into the search engine. This is a text search engine. We're now using it on non-text. The indicator is not text, it's a thing. It's an apple. So whenever anybody walks in with a history containing an apple, we will do a search against the search engine saying, what things have apple as an indicator, and we'll get back puppy. Yeah, good.
Do you care which occurrence happens first?
Ooh, that's so good. Generally not. I mean, I do care, but I don't care. The reason I don't really care is because my data is probably imperfect. You might have come from somewhere else. Suppose you buy A's and then B's and then A's and then B's. So I should care that A leads to B and so on. But if you bought the first A somewhere else, I'll see B's first. So I often will see data jumbled just because your life is not as simple as it might be. Also, suppose you buy, I don't know, the third Star Wars movie, whether that's number 6 or number 3, I don't care. What if you buy not the first one first, and you go, oh, that's kind of cool, my grandparents watched that. Now you go buy the 5th one or the 2nd one. You buy them out of order because you get interested in some for some other reason. And so things happen out of order, even if they have a very good ordering. So as much as anything, I don't care. I'll recommend it either way. If the things have a strong ordering, the system will eventually kind of pick that out, and it'll work out. Yeah.
So what happens with time dimension here? Because
I just threw it away.
I might like puppies now, but I don't like them.
Okay. Well, generally the way I handle time in these things is the query is a fairly recent view of what you've done. And the co-occurrence I usually do within, say, months or a few months. And so it's time bounded too. And so the co-occurrence of apple and puppy means that there's a large number of people, anomalously many, who like apples and puppies at the same time. And then the fact that apple is in your history means that you recently liked apple. If it quits being in your history because it's not recent anymore, then we quit recommending puppies. So I've averaged away time, at least in the presentation here, but by just limiting how I do the windows for the analysis, I've included some of that temporal analysis. And then by limiting the query size, I've introduced it kind of in the back door again.
Is it worth going back and studying how flexing that time dimension matters?
Depends on how much time you have to spend on stuff that doesn't much matter. Now, by doesn't much matter, I mean less than 100% improvements. Yeah.
But are we not also causing causation that we are feeding ourselves that apple is no longer required? Because if I've stopped recommending the apple with a pony,
Well, I only had 4 things to talk about here, and so it's very difficult to explain too many subtleties. But yes, it might be that people buy apples over and over again, but they never buy puppies over and over again. And so think about razor blades. And you begin to see that different kinds of behavior and different items have different properties. If I buy a particular razor blade, a Gablordo razor blade, I'm probably going to buy the same kind of razor blade again. It'll grow, and I'm going to want it. And so, just a moment. And if I buy the competitive Grosnak razor blade, I probably won't buy Gablordo because people tend to be fairly loyal to that. So the competitive razor blade is an anti-indicator for the primary thing, and the thing is an indicator for itself. I'll see it in there. Now I could throw away multiples, or I could consider them depending on my market, my place. But there, with razor blades, they self-recommend, and the competitors anti-recommend. Take movies, though. If I see somebody bought Finding Nemo, then there's a very bad chance they'll buy it again. And there's a very good chance they'll buy Toy Story. So these competitive movies that are same genre, same interchangeable, roughly interchangeable, no 2-year-olds in the audience, I hope. These things cross-recommend, but they anti-recommend themselves. They're exactly the opposite of razor blades. And then we can add other behavior, like reading reviews. If you read the review of the competitive movie, you're likely to buy the competitive movie. If you read the review of the same movie, you're very likely to buy that same movie. If you read the reviews on the razor blades, you're nuts. Nobody does that. You're a QA team or something. You're never going to buy anything. Okay? So the behaviors are different. The indicators are different. The nuance, there's lots of nuance here, but it'll all come out in this co-occurrence wash. Yeah.
it's kind of little echoing what you said. So would you be a way to be able to factor some serendipity here? Because
This is a serendipity engine.
I mean, I know
Especially after we add
this is
iterative.
based on the premise that the user has, but a user might have some random. So if you can some analyze certain days and specific, I don't know, features that the user might not generally pick, but you might just someday, if you do an analyze of all this history, you might find some patterns which is normally not even normal range.
This has many, many surprising properties. One is that rare things, when they co-occur with other rare things, pop out of the statistics very strongly. And so if I have a very idiosyncratic audience, I will learn about their idiosyncrasies very well. This is the kind of serendipity or the unusual behavior things that I think you're referring to. With music, we had this situation. It's among this music that just sounded like noise to me. It was forms of metal. There were clearly groups that didn't listen to each other's music. And I asked somebody who liked that kind of music, and they said, oh, this is black metal, and this is death metal, and this is something else metal, you know. And so like one of the groups was named after an axe murderer in Finland. Another group from Norway instead sang Norse sagas to heavy metal music. And then there was this depressive Northern English type of metal. I can't remember all the names. I couldn't stand the music. I couldn't understand it. I didn't hear any differences. But to the people in those communities, it was night and day different. And so this system finds those sorts of things out very clearly. We could see differences in immigrant communities. So the Vietnamese community on the West Coast and the East Coast listened to different music. And we could see that. And then they listened to some of the same music. And so these things in forms of music that we had no understanding of, we would see. One of the best demos was a music executive would come in. I'd say, what band were you in high school? They would say it, I'd type it in, and bam, it would tell us what music they like. Very, very strange corners can be found by this sort of engine. Very, very effectively. But anyway, let's continue. It's exciting and fun to play with this. And it's very easy to play with it because text search engines are so easy to do, and you probably already have one. Here's another example. Now remember I mentioned different kinds of behavior? Well, if you think about it, typing words into a search engine is a behavior. Viewing videos is another behavior. We can cross from one domain to another. Now I'm not talking about looking at the words people type as words. I'm not talking about matching them to text. I'm talking to say they are just behaviors. So I take what they type, what words they type, what videos they watch, I cross those and find out what connects. I started with 1 million videos that had no videos by Paco de Lucia. Paco de Lucia was originally flamenco guitarist who very quickly moved into kind of jazz-tinged sorts of things and invented the style of music that he called New Flamenco. Very popular in Europe. He died a few years ago. So the ordinary search would find, because this is user-generated or user-stolen content, it would find hundreds of examples of Spanish daytime television, Hombres de Paco. Those are terrible results. But the recommendation-based search would find this. Well, here's the daytime television, and here's the recommendation search. The top hit is a Spanish classical guitar piece. Well, look at the guitar. That's a semi-acoustic jazz guitar. So it found Spanish music being played in a jazz style. Score. You know, this is cool. I knew there was nothing correct in this thing, but that's almost better than correct. The second hit looks really bad. It's these women dressed in black. CUD is the name of that group. They are a flamenco dance troupe, and they're dancing the bulería, which is a flamenco dance. That's not so bad. The third hit is the same piece of music as at the top by Vicente Amigo, but now it's being played on a classical guitar. The fourth hit looks really bad. It's Van Halen playing a classical Spanish guitar riff during concert. 17-second clip of saying, look at him play classical guitar. This is pretty good. And then the bottom hit is a guy imitating Paco de Lucia in his dorm room. It's like somebody built this entire ontology of knowledge that, like, bulería is a kind of flamenco dance is played with flamenco music is related to what Paco de Lucia played. And indeed, people were building that ontology, all of our users, by doing what they loved, which is listen to music, watch videos, and things like that, and ask for what they want. They didn't necessarily find what they wanted, but they watched other things. And here, for instance, you asked about order and time. How should I look at ordering and time? Maybe somebody liked this jazz-flavored Spanish music before they asked for Paco de Lucia. Maybe they liked that after they asked for Paco de Lucia. I don't care. All I care is there's a connection. And so I'll show it to them in the right order or the wrong order, just in case they weren't paying attention the day it was shown. So this is an example of where the temporal order, I don't really care, because I'll just play it however it works. So anyway, this is search abuse squared. I started out by abusing a text search engine and putting behaviors in it, and then the behaviors were text. So I was doing text search using a recommendation engine implemented on a text search engine. So this is definitely search abuse squared. And it worked really well. We even could build a thing where we just put a logo on the website. We didn't know what it meant. The first 20 people would get a little under construction sign. And after that, we showed people whatever we would recommend to whoever clicks on that. So it's circular. If you clicked on it, you must be a person like the people who click on it. So we'll show you what those people like. We put up a thing that said fast cars, and within a few minutes, it was showing all of the teenage boys who were clicking on that American muscle cars with girls in bikinis on them, which is what they wanted to see. It wasn't necessarily fast cars, it was just what the people who clicked on fast cars wanted. So anyway, that was fun. Now here's something very actually similar to this, but this one is worth real money. These others are just fun. I should take my hat off if it's not going to make money. But anyway, the idea here is, you remember what happened with Target 2 years ago? What happened there is their heating and ventilating repair guy got a log into the system for whatever reason. They didn't have segregation on their networks. Somebody got somebody to work for that contractor and then was able to inject something into the antivirus checker so that the updates to the antivirus system to the point of sale terminals injected a monitoring system. And then they just uploaded from all the point of sale terminals all of the credit cards being run. The alarms went off, but of course the alarms were going off all the time anyway, because they had a very naive sort of alarm system. And so for several months, 40 million people's credit card data was siphoned off and given to thieves. And there's actually a significant amount of fraud from that. But how do you figure that out? So the situation is we're going to be sitting at a bank. We have no visibility into Target or any other merchant's behavior. But we want to protect our users from fraud that occurs. How are we going to do that? So this is a simulated set of data here. And in this simulated data, merchant zero. You know, in epidemiology, the origin of the epidemic is called patient zero. But the origin of this fraud ring is called merchant zero here. Merchant zero has been compromised. For 3 days, accounts are being stolen there. Only a few hundred. After that, there's an exploit period where the probability of fraud is much higher among the compromised accounts than in other accounts. We want to find merchant zero. Here's a picture of the simulation. During the compromise period, you can see the number of compromises goes from 0 up to 500 a day, and then drops back down. During the exploit period, the baseline level of fraud, there's of course fraud happening in other ways, goes up a bit. The estimates currently are that about half of credit card fraud is due to merchant compromise. That was before Target. It may be higher now. And the fraudsters are beginning to do very subtle things. If you had something on your credit card, I have to find somebody who doesn't look like they paid a lot of attention. If you had a $10 fee from some internet thing that you didn't quite recognize, would you call the credit card company or would you just bite it? $10. You're going to go through and file a fraud affidavit? No, it's just not worth it. It's barely worth it to call them to get the $10 back. Well, the fraudsters depend on that. So they don't even get reported as fraud. So let's figure out what happens here. That's how we generate it. That's for you to read later. But remember, this is not a very realistic simulation. There are no details of the fraud. There isn't even an amount of purchase. It just says, which merchant is it? There's no detail about how the fraudsters got the data, what they did with it, how they caused it. No details on the transactions themselves. No idea what was bought, just where it was bought. No idea how much was bought. No details on the fraud models that are, see, something is detecting that fraud. No details on any of that. The idea here is kind of interesting. If we build a machine learning model, we take data, we have a training algorithm, build a model, and we move it into production, then we give it new data. Now, it's going to do things right, and it's going to do things wrong. It's going to have false positives and false negatives. And so we're going to get scores coming out of that, key performance indicators, KPIs, based on how well it's doing. Somebody outside, somebody who's building a simulation like I did, is not going to be able to see any of that stuff. We're going to be outside the perimeter. They cannot give us data. They would like to give somebody like me who might have some bright spark of an idea, or the thousands of other people who might have an idea. They'd like to give me data so I could try it out, but they don't dare give all those people data because the fraudsters would figure that out pretty quickly, and they would pretend to be people building new models. So outside collaborators cannot see the secure data, and therefore they cannot build good models. An academic, for instance, can't really build a good model building algorithm because they can't see the real data. The people inside can't make use of academic research because they can't give them the data. We have a real problem here. But what we can do is we can take the way that the system behaves on live data and the KPIs it produces, how it fails, how it works, and then we can generate fake data, not so that the fake data looks like the live data, but so that the signatures are the same. Say the false positive rates. The false positive rates at different score levels. This turns out to be much, much easier than making realistic data. It doesn't even have to have the same dimension. It just has to be tuned to produce the same failures. Take a simple example. We had a customer, they called us up, they said, Hive, which is a query engine, Hive broke. We said, can you send us the data? They said, no. Can you send us the stack traces? They said, that might contain input data. No. We said, could we try it on the machine? They said, no. These are all legally correct answers. We said, what do you want us to do? They said, fix it. They're customers. That's what customers say. So all we needed is random data that matched the failure signature that caused roughly the same failure. That's the only KPI we needed. We built kind of plausible data here and turned knobs on the generator until it caused a failure that looked like what they were describing, sent them the generator. They said, yes, that's the problem. And then we had data outside the security boundary, like this. We were generating our fake data. They generated fake data and verified that the failure signature matched. And we generated data. And, oh, it's obvious. The optimizer in Hive was wrong. It had a fixed length array. It just overwrote stuff. It was easy to fix once we had a failure. We could even scale it down very carefully. You couldn't just try small data sets because you had to have just the right balance of data sizes in order for the optimizer to try to make the same wrong optimization. Now, we can do this with machine learning as well, like I did with that simulated compromise data. So we can match the number of users, the number of merchants, the number of transactions per user, the skew. So some merchants are more popular than others. How much more popular? We can match the amount of fraud that we see, the amount of fraud due to compromised merchants, and the spectrum of scores. We can match all that. And in practice, here's how it works. This is the analysis of the simulated data. There are not a whole lot of merchants here. I just got lazy. It's on my laptop, that sort of thing. The flight was about to end So, what do? Run as many as I can. So that's the compromised merchant right there. Stands way up out of the noise, right? Well, at the end of a workshop with a real customer, we tried showing them this stuff again, and this is their data. You see that little hoop right there? There it is again on the live data. Even the anomalies, as it turns out, the little tiny score anomalies were replicated in this simulated data. And this purple thing up here, standing even further up out of the noise, were really bad guys. And repeating that, really bad guys. They called the Secret Service. Secret Service checked on them. This was a restaurant right next to the CTO's house where he liked to have a beer after work, which had been completely subverted and was a skimming operation. Just out of the blue, we were able at a small bank to find real bad guys. The cool thing is this is a recommendation engine. It's using the same co-occurrence statistics as the ponies and puppies stuff. So really, really simple logic, 5 lines of code, and you can find real bad guys using these techniques. These, I think, are important algorithms because we can do important things with them. So we live in a golden age right now. All of this data is coming at us, and we now have very simple things that we can do to find these things. We used to have low-hanging fruit. The tree just came down lower, and we have gobs of low-hanging fruit again. There's just all kinds of things we can do. You've seen several examples, and you can get more information at this web link. The things we have there are books. There's, there. We have little, oh, these are books. See what's on the cover? It's a pony. Anybody want a pony? Yeah, well, I'll sign some books. There's also in it a flyer which shows the other 4 books in the series. In fact, there's a 5th book now, but you can all get them at this location. And let's have some after now questions. Sorry, I didn't keep track of who was asking questions before, but the next 2 good questions can have a hat. Yeah, you don't count.
I know, I wouldn't want the hat.
Yeah, you look like a fool wearing 2 hats, right?
The replication of the data or the generation of simulated data, can you generate all kinds of data or is it just numerical?
So this was generated by a tool called LogSynth, which I have on GitHub, log-synth. It's open source, and it takes a schema. It's not really a database schema. It's a random number generated schema. And it produces data in that style. It generates nested data, so it can generate very complex transactional structures and things like that. And it's very easy to extend because it's also a programming framework. So you can, this point of compromise is one of the emulators. There's a vehicle, a VIN number emulator that knows all the Ford and BMW factories and engine sizes and things like that. There's another one which is commuters. So it picks a home and a work location, and you either drive to work or you do errands, or then you come home if you're at work and things like that. And it emulates street or highway driving down to RPM and throttle levels and speeds and so on. So it's very easy to add to things like that, and it's very easy to use it as it stands to generate relational tables that link together or transactional sequences like buying stuff. So yeah, that's open source and very, it's simple. Everything I do is simple now. I refuse to do complicated stuff because I'll have to do it forever. Yeah.
So,
Getting it ready.
My nephew a baby present.
Yep.
And then suddenly, on my recommendation, for a while, they're seeding it with other children's toys and stuff. And I don't care.
Is that bad?
It was a one-time occurrence. Right?
You're never going to give him a present again.
I don't want to look at all the other baby stuff. Is that?
I'm going to tell your nephew you said that.
Is that like kind of filtered out through just the time window?
Time window should
Yeah,
have
that's
that.
just it.
Yeah.
It's just going to age out.
Yeah.
If I don't.
If you write it well. That's a duplicate question.
Would it be beneficial to opt out of
you've had users tell you find this one thing one time.
Let users edit their history? Sure, why not? I mean, they're the users, right? If they just don't want you to know that you bought that thing, I don't care what their reasons are. I want to make them happy. I think it'd be silly not to. Unless it takes a whole, can you help her? Sorry. It's probably better than if I hit her. But I don't want to tell users what they can and cannot do. Most are going to be too lazy to do that, or it's going to be too hard to find out how to do it. But if somebody really wants to edit their history, I think that's a great thing. They may well have clicked on something by accident. It may be really embarrassing. I mean, a lot of ads try to make you click on stuff that would really not be what you wanted to be known for.
I think it's fine to edit
history.
This isn't the FBI.
Well, would it also improve your results though? You're learning things about the people.
Yeah, really, I could use what you deleted from your history to learn about you. Yeah, I could put it in another pile. In fact, I would typically not forget anything if I could possibly do that. But I wouldn't recommend to you anything based on that. If you've got a nephew, by the way, and you don't like the hat, you can, without even me recommending the next hat, you could give it to them.
Okay, in the back.
I thought the idea of doing the sketch was very interesting, and it looks like you get there with 2 steps. So you can log in, and then you get your K in the next step.
Yeah, so the first step is doing the sketch.
Right.
You get to the sketch in one step.
Right.
And then you cluster or do whatever you want with the sketch.
So my question would be, are there any instances where it's practically efficient to do that in more than 2 steps? I mean, do you lose anything by doing it in 2 steps? Are there times where you might want to do it in 3 steps?
So there's times when you might want to do it kind of like in 3 steps. Like you might want to do pieces of the input and produce a sketch on each one, and then combine the sketches and combine the sketches of sketches, and then cluster that. And that's kind of like 3 steps or 5 or something. It's more than one level, and the same guarantees apply. In fact, even if you do it a little carelessly, you get better accuracy by doing it that way.
Yeah.
How do you create a...
Don't warn the guy. Oh, almost.
How do you create a recommendation game for a person with dual personality?
Dual personalities like me? Well, how do I build that? It doesn't really matter, because if I have 3 personalities in my recent history, then 3 kinds of things will match. And I will have a lot of results from the search engine that's giving me recommendations, and I will try to not let it flood with any particular kind of input. I'll do anti-flood. So I might give me 5 jazz things, 3 classical, 3 Americana, and 3 Bollywood. But I wouldn't want to give me 30 of the jazz. And by doing the anti-flood, what we do is we kind of play a portfolio game on that. I might be wrong on the most strong recommendation. And if all of the top hits are the same, if I'm wrong on one, I'm wrong on all of them. But if I limit it to only a few of those, if I'm wrong on the first, I'm wrong on the first 3, but I might be right on 4, 5, 6. Oh, if I'm wrong on the second thing, I might be right on 7, 8, 9. And so I get this portfolio effect, and I have a much higher chance of being right about something in the top 20 this way. And I also serve people with multiple personalities. People with multiple personalities are sometimes called families. I can't tell the difference, sometimes they act like a 2-year-old, sometimes they act like a really bored 37-year-old. I can't tell if it's one person or not. I shouldn't really care. But the same way, I should show them some 2-year-old stuff and some period drama or something like that. A little bit of Downton Abbey. The 2-year-old's not going to like it, and the 37-year-old's not going to like the 2-year-old stuff. But one of those 2 is likely to hit. And so multiple personalities are not the exception. They are the rule. People do not have simple personalities. They have complex complex combinations of tastes and histories and preferences. Anything like, a lot of marketeers say, I'm going to do segmentation. You are suburban. I am urban. They're going to say one thing about me, and they're going to be wrong about 9 things about me. That's a very wrong way to do this. It's much better to say there's lots of complexity and there's lots of pieces to her, not just one thing about where she lives. I'm sorry if you don't live in the suburbs, but it's just a guess. And you can see how bad it could be to be wrong there. Yes?
So on the sketch, is there a sensitivity to the number of points in the sketch, or?
There is, but if we're doing a good sketch, a safe sketch, we will have enough points in the sketch and a few more to be very safe.
Because it doesn't, it's not a
If the sketch is twice as big, let's talk about how big it has to be. Let's cluster 1 billion points. And we want to eventually get 1,000 clusters. The log of 1 billion is like 30-ish, hand wave. And I want 1,000 clusters out. So I want 30,000 things in the cluster, in the sketch. What if I keep 100,000? 100,000 points, each at 8 bytes. It's a megabyte. Who cares? I really don't care. Keep 200,000, just, party time. It still is tiny. It's less than 2 megabytes. And so I can afford to multiply it by 10. Take 100 billion points. I just increased it by 10%. Just don't care. So that's the trick of it, is that we get nice guarantees theoretically, and then we say, a lot more. And then we're very safe. So it's only sensitive well below the theoretical guarantees, and we're exploding well above that just to be safe. Here's a virtual hat. That was a good question. Okay. Oh, you? Yes.
Maybe in the end I was a little confused when you're talking about the security breach. So hypothetically, like say the target situation, because it just happened that one day, so it might be easier to people to realize, sudden big volume of data going on. But if some kind of breach is very gradual, and some people take certain information a small period of time, little by little, in that kind of a breach, what kind of model?
So I think what you're talking about are these advanced persistent threats. And in the most extreme case, the threat, you get a penetration, you get lateral penetration, and then they go quiet. Very, very quiet. Or they piggyback on very innocuous traffic and move just little bits out. There is some level at which you cannot detect this. And there are some situations where it is so important that you must be very, very vigilant there. I saw recently a cryptanalysis of a worm called the flame worm. And what they did, these people were obviously very dedicated. They compromised, they counterfeited a Microsoft root certificate. Didn't know you could do that. And then they counterfeited Microsoft Windows updates. And that's how they propagated the worm into very secure areas that were air-gapped. Impressive. And then they also had a means of communicating back out through the handshake for the updates. And so, and then they did very little else. Now that's hard. And that's very hard to detect. But in the case of Target, some of the MapArc customers actually detected that very early on and were able to lock down everybody who had an account at Target early on. Now, Target wasn't listening to all the false alarms and then the real alarms coming in, and so it persisted for months until somebody finally convinced them that it was very, very serious. But this was detected relatively early by techniques not so very different from what I showed you here. And in other situations, you could do very simple stuff if you have enough data. Yeah. So see, we could even build an anomaly detector on top of on that point of compromise thing. When suddenly we see something popping out of the noise, we know there's been some compromise.
Is there any way we can distinguish between normal range or, let's say, Thanksgiving season, I mean, the data will go. Either way, there's no visual.
You should have been at the talk last night when I talked about exactly that, training on Thanksgiving and detecting on Christmas. It was exactly the example I used. It's last night, and I'm so sorry, but you can find the slides online. I'm so sorry it was last night, not tonight.
Yeah.
Sorry if I missed this, but what clustering algorithms can you use to build Sketch? Is that all right?
Sketch is built using a very simple algorithm. It's close to an algorithm called the DP means. That was work by Michael Jordan and another person. Jordan was second author. But it's very simple. So in k-means, I would find the nearest centroid and assign to that. And I would have a fixed number of centroids. In dp means, I find the nearest centroid, and if it's closer than a threshold, I attach to it. If it's further than a threshold, I make a new data point. And then there's a collapse mechanism which increases the threshold if I get too many sketch points. That's it. It's a very, very simple thing. And it even works with an approximate nearest centroid search. So that's how it gets fast. I'm busy stealing somebody's pen. I should put that back. Yeah? The latest stuff coming from MapR? Well, you saw it. It was hats. We have some very cool stuff. We have a document database that's built into the bottom data platform. We have all kinds of performance improvements coming out. We've now in the lab well exceeded 10 gigabytes per second per node of I/O performance. We have scalability improvements coming out, so you can now handle as many as hundreds of disks per node. So all of the things that we've been doing for years, which is making the data platform underneath big data solid, secure, easy, dependable, fast. That was where we started. We've been continuing that and increasing the lead we have in that technology. And I shouldn't say too much about that. I'm happy to talk about it way longer than anybody here wants to hear. But tonight's kind of a hats off night. It's talking about other things, but I'd be happy to talk afterwards about some of the cool stuff we could do. And Jay actually lives here. Raise a hand. He has a MapR on his shirt, but no MapR on his head.
Okay, something now. Yeah, I think let's close the questions. Let's start by thanking Ted for